Hello and welcome to NASA Science Live, an opportunity for you to come behind the scenes and to get to know your space agency. I'm your host, Sophia Roberts. This show is really all about you being able to interact with NASA scientists and to get your questions answered. So please visit us on Facebook or Twitter and ask us a question using the hashtag AskNASA, or leave a question in the comment box wherever you're watching this. Let's get started with some of the latest news from around the galaxy. Scientists were surprised to learn that near-Earth asteroid Bennu is not only more rugged than expected, but it's actually erupting plumes of particles from its surface. Two facts that are sure to give spacecraft navigators a little asteroid indigestion. But never fear, NASA is up to the task of collecting a sample from this asteroid and sending it back to Earth. In other news, the agency rolled out its Moon to Mars program that will see astronauts living and working not only around the moon, but on it. Before you know it, we'll all be like Matt Damon, making space potatoes. But maybe let's bring our own fertilizer. All right, moving on to matters of international appeal. NASA signed on an agreement with the Brazilian Space Agency on an upcoming mission in the form of a teeny-weeny satellite. It's called a CubeSat. This small spacecraft, cutely named Sport, is about the size of 2 loaves of bread and will investigate 2 phenomena that happen above our planet that disrupt radio communication systems, satellite technologies, and even GPS signals. I don't know about you guys, but I need me some GPS. I honestly wouldn't have even been able to find the studio without it. So, go Brazil! All right, that is all the news we have for now. Today's episode is all about interstellar space, and the topics we'll cover will take you to the edge of our solar system and beyond. We'll show you how big our galaxy is, check in on the Voyager spacecraft, and explore the region beyond our bubble. And you'll meet a really special student that is helping us hunt down planets that orbit other stars. So just to give you guys some basics, interstellar space begins where the sun's flow of charged particles ends. And we call this bubble of particles the solar wind. It extends well beyond Pluto's orbit, but not all the way to the edge of our solar system. Our solar system actually continues all the way out to the Oort cloud, where billions of comets still cling to the sun's gravitational pull. But remember, when we enter interstellar space, and even when we leave our solar system, we're still within the Milky Way galaxy. So, just how much do you think you know about our cosmic neighborhood? Let's find out. Join me and 2 astrophysicists as we play That's a Big Galaxy! All right, our first contestant is an astrophysicist and football lover, Dr. Nicole Colon. And our second contestant is an astrophysicist and sci-fi nerd, Dr. Aki Roberge. Thank you both for joining me.
Thank you.
Right. This is how all of this is going to work. If you get our questions right, yeah, but if you get them wrong,
Whoa.
So no pressure here.
None. Okay.
Great. All right, question number 1. If the Earth was the size of a basketball, the sun would be A, 20 feet in diameter, B, 1,000 feet in diameter, or C, 100 feet in diameter.
Okay.
So basketballs like this.
So that's about that big.
Yeah.
Okay, so Earth's across the sun. So you can put, as I recall, about 100 Earths across the sun. So
Okay, I'll take your word for it.
Call that a
Sounds right.
Call that a foot. So 100 feet. Was that one of the choices?
Yes.
Okay. That was easy.
It is 100 feet in diameter. I mean, the sun, we really know, is huge, but how big is it really? And to be more precise, since we do have some scientists with us, it would be about 109 Earths that fit across the diameter. And it would actually take 1.3 million Earths to fill the sun's volume.
That's a lot of Earth.
That's a lot of Earths. All right, let's move on to question number 2. If the sun and the Earth were separated by 5 pieces of toilet paper, how many would separate the sun and the boundary of where Voyager 1 crossed into interstellar space? Would we have 18 sheets of toilet paper, 203 sheets of toilet paper, or 602 sheets of toilet paper?
Okay. So toilet paper, yay big, yay long. Well, actually, all right.
Doesn't matter, right?
No, it doesn't
Actually,
matter
yeah.
because we
Yeah.
know the distance from the Earth to the Sun is what we
5.
call is
Oh.
5 pieces of toilet paper, and that's like 1 astronomical unit,
Right.
which is literally what we define as the distance from the Earth to the Sun on average. And Voyager is about 100 astronomical units outside, away from the Sun. So if you just do conversion, 5 times 100 is about 500, and I think that was close to one of your
Pretty
answers.
close.
Yes,
Okay.
it really is 602 sheets of toilet paper.
Close enough.
And just to give you guys a little more context, using this analogy, Mars would clock in at 7.6 pieces of toilet paper, Jupiter would all the way be at 25.9 pieces, and then you would need a whole nother roll to get to Pluto at 196.2 pieces of toilet paper.
That's a lot of toilet paper.
It really is. But I hope this helped you guys all understand really sort of how large our galaxy is.
That's right. And that's just our solar system, right? So
Yeah.
even the closest star is much further away from that.
Yeah. And yeah, though, but actually I wanted to kind of make one point though here though. So for the viewing audience, I'm a professional astrophysicist, and I would normally solve questions like this exactly the same way you would. I would type them into Google. Okay. So for me, the most important part of my job is actually more about coming up with those questions that actually, the right questions to actually push the boundaries of knowledge into the unknown. And that's the actually really exciting part and the fun part too. So.
That's right.
All right, I want to thank you both for participating in our game show.
Thank you.
Thank you so much for playing That's a Big
Thank you.
Galaxy. And our astrophysicists will be returning later on. So please send us your questions using the hashtag AskNASA. All right, so as you just heard, our solar system really is huge. In fact, the Voyager 1 and 2 spacecraft, both which launched in 1977, needed to travel for 35 and 41 years respectively before they even left the boundary of our sun's influence. I mean, at their current speed, it would actually take the Voyagers another 75,000 years to reach the next nearest star system, which is Alpha Centauri. So the fact that 2 spacecraft, which were built in the 1970s and located more than 11 billion miles from Earth, are still working and communicating regularly is simply mind-blowing, for me at least. So in a moment, we're going to be joined by an expert from the Voyager mission, live from Mission Control at NASA's Jet Propulsion Laboratory in California, which they refer to as the center of the universe. But first, let's take a look at some of the amazing milestones of the Voyager 1 and 2 spacecraft.
3, 2, 1. We have ignition and we have liftoff. We have liftoff of the Titan Centaur carrying the first of 2 Voyager spacecraft to extend man's senses farther into the solar system than ever before.
They were launched in 1977. That's really 2 generations ago. You can think of what the technology was. Your smartphone has 200,000 times more memory than what the Voyager spacecraft have.
Voyager 2 was the one that was chosen to do the grand tour, that is to fly by Jupiter, and then Saturn, and then Uranus, and then Neptune. Voyager changed our view of the solar system, really.
Every planet we flew by, we got more questions than answers. They whet our appetites for more.
We were on a path we hoped to get to reach interstellar space while we still had power on the spacecraft to transmit the data back.
The team has been looking forward for this for a long time and really working hard in an engineering sense to make this happen. It's exciting that we've been able to get it into interstellar space and to keep all the instruments on.
A real opportunity on Voyager 2 is because we have a working solar wind instrument to measure interstellar wind for the first time directly. The wonderful thing about the journey is it's still discovering new things because it's going where nothing has been before. And they will continue that journey for billions of years, orbiting the center of the Milky Way galaxy.
All right, I'm really excited because we are joined by a Voyager expert, Dr. Suzanne Dodd, who's calling in from NASA's Jet Propulsion Laboratory in California. Hello, I'm really excited to be talking to you, so thanks for joining us.
Thank you for having me on.
Yeah, so can you please tell us where you are right now, because I can see behind us that like this looks really cool. So can we just start off with saying where you are?
Yeah, sure. The room that I'm sitting in is called the Mission Control Center. It's here at the Jet Propulsion Laboratory. And what happens in this room is it's where we control the very large antennas on the ground that we communicate with the deep space missions, so that all the data that comes back from NASA's spacecraft that are out in the planets or beyond, such as Voyager, that data comes down through these deep space network antennas and into this room. So we really are the center of the universe.
And can you tell us where the two Voyagers are right now?
Sure. Voyager 1 is up and out of the plane of the planets. It went by Jupiter and then Saturn, and it went up and out of the plane of the planets, whereas Voyager 2 went by Jupiter, Saturn, Uranus, and Neptune, and down and out of the plane of the planets. So Voyager 1 is approximately 13.5 billion miles from us here on Earth, and Voyager 2 is approximately 11 billion miles from us here on Earth.
And are we communicating with them right now or soon?
We certainly are, yes. For the Voyager 2 spacecraft is communicating with our deep space network that's located in Canberra, Australia. It's using the large 70-meter antenna dish.
And how do you know that we're communicating with them right now? Is there a way to see that?
Well, yes, you can see it. Actually, any of the viewers can see it on a website called DSN Now, but it's on the screen right here. You can see in the lower left-hand corner there's a VGR2 that's tracking under DSS 43, which is the large antenna in Australia.
So I'm sure that all of you out there right now are curious about the Voyager space mission. So I'm just going to turn it over to you guys in the public so you can ask our doctor some questions. So I'm hearing that Bruno from Twitter is asking, what kind of data are we expecting to gather from the Voyager Interstellar mission?
Good question. Voyager is really like a weather satellite traveling through interstellar space, and what interstellar space is contained of, it's dust from other stars. So what Voyager is measuring is the density of the dust and plasma that it's traveling through, the directions that these dust particles are coming from, and also it's measuring the magnetic field that Voyager is traveling through.
All right, amazing. All right, and Carlos on Twitter is asking, is the speed of Voyager 1 and 2 changing in any way? And if so, why? And what are the implications if they are?
Well, actually, the speed of Voyager 1 and Voyager 2 is constant. They're approximately going 35,000 miles per hour. Voyager 1 is a little faster and Voyager 2 is a little slower, but their speed was set by the last planet that they left. So after Voyager 1 left Saturn, its speed has been constant since then. Similarly, after Voyager 2 left and flew by Neptune, its speed has been constant since then.
All right, Mapatag on Twitter is asking, has there been any wear and tear on the Voyagers as they've traveled through space?
Lots of wear and tear. These spacecraft are over 40 years old, so things have broken. And we have to work around that as engineers. We have to figure out clever ways. We can't go to the spacecraft to fix them, so we figure out clever ways to work around what no longer works on the spacecraft. And it's truly remarkable that we've kept these spacecraft going for over 40 years.
All right, thank you, Suzanne, so much. That's all the time we have right now for the Ask NASA. So, but we will be returning to that later on. So let's get back to some of our science. Please keep sending your questions our way, though, because we will be answering some later. But I do want to just recap on some of the incredible numbers that we've talked about so far, because, I mean, it's just amazing that it's going to take another 75,000 years for Voyager 1 to fly anywhere near another star. And the planets outside our solar system, even in our cosmic neighborhood, are just really, really far away. So it's actually remarkable that spacecraft can even study them. Which brings me to TESS, NASA's Transiting Exoplanet Survey Satellite. And it scans the sky looking for planets that orbit other stars. But let's take a minute to understand exactly where TESS is looking.
For the longest time, space seemed like a big, nearly empty place, and we were really only familiar with our home, Earth. But as we learned more, we realized there was actually a lot out there, including planets orbiting the Sun and even other stars. Enter Kepler, a space telescope that radically changed our understanding of planets outside of our solar system, also known as exoplanets. In finding thousands of new planets, Kepler showed that there are more planets in our galaxy than there are stars. But Kepler looked at only a small fraction of the sky, and many of the planets it discovered are too far away to study in much further detail. And that brings us to TESS, our newest planet hunter. The Transiting Exoplanet Survey satellite works like Kepler, and over the next 2 years, it will scan almost the entire sky. By looking at closer and brighter stars, TESS will find and measure the sizes of dozens of small nearby planets, best suited for detailed investigation by powerful telescopes on the ground and in space, like the future James Webb Space Telescope. And by doing that, we might finally begin to answer the question of whether Earth is alone, or whether there are worlds out there like our own, small and rocky, covered in oceans and dense clouds, or even, possibly, capable of supporting life.
TESS project scientist Dr. Patty Boyd. Thank you for joining us, Patty.
Thanks for having me.
And as we just learned a little bit about TESS, but I want to just ask you, where is it looking?
So it's really exciting to be talking about TESS when we're celebrating Voyager, because as the Voyager spacecraft kept going out and further away from Earth, TESS is very different. TESS is orbiting the Earth. So we come back very close to the Earth every 2 weeks, and we return our data to the ground. And what we're doing is we're looking at our nearest neighbor stars, so the brighter stars in the sky, which are typically the closer stars. We are looking at those stars, searching for planets around them. So those are called exoplanets. And when Voyager was launched, the only planets we knew about in the entire universe were the ones in our own solar system. But TESS, one of our newest spacecraft, launched less than a year ago. Now we know there are planets everywhere in our galaxy, and TESS is taking that next step to find planets around our nearest neighbor stars.
So we're still talking about things inside of the Milky Way galaxy at this point?
Very much so. Really just taking those first few steps from where we are in the Milky Way.
So still very much in our cosmic neighborhood, right?
Perfect, yes.
Yeah. Which is amazing that we can still find so much so close to us. And then there's so much further away even to consider later on.
Right.
Yeah. So how does TESS look for and find other planets? Like what process is
So
that?
it uses the same method that Kepler used. It's something we call the transit method. And Kepler gave us a great answer about the Milky Way. It told us that planets are everywhere, and there are more planets in the Milky Way than stars. So that means that TESS can take the next step and determine where are the closest stars. And the way both missions do this is they monitor the light from many thousands or millions of stars all at once, and they're measuring how bright the light is, and they're looking for a very tiny dip in the light called a transit that happens if the system is perfectly aligned between the observer and the sun, the star. You see a tiny little dip in the light from that star. That's called a transit. The planet goes around, you don't see anything, and the next time it comes around, you see another little transit, and that tells you the orbit of the planet. And if you know the orbit of the planet, you can tell how far away it is from the star.
Just a little blink in that light, right?
It's a very tiny blink. You have to have a very precise ability to measure the light, because we're talking about hundreds of parts per million. And actually, the smaller the planet, the smaller the dip. So we actually get some information about the size of the planet just by measuring the dip or the transit.
And so, of course, everyone's always wondering about potential life. So are we looking just within the habitable zones or other ones, or where precisely are we, concentrating our efforts?
So TESS is basically searching for transits of anywhere between less than a day length. So those would be planets that are really zipping around their star, very close to the star. They're lava worlds, all the way out to planets that would orbit on, say, month-long timescales. So around small stars, that would be far enough away that they might be in what we call the habitable zone. And that's a very special area near a star where the planet isn't too hot that all the atmosphere would be vaporized or blown off even, and it isn't so far away that any liquid water that were there would just freeze onto the surface. It would be in that special Goldilocks zone, not too hot, not too cold, but just right for liquid water to pool on the surface, for ice to be at, say, ice caps if they're there, for vapor in the atmospheres. So TESS will find all kinds of planets, and some of them we're hoping will be in the habitable zone.
All right, wonderful. Well, now it's time to get your questions answered. And if you remember any questions that you had before, let us know using the hashtag AskNASA. Or if you're just tuning in, this is NASA Science Live, where we're talking about interstellar space. So I'd like to invite back Dr. Aki and Dr. Nicole, who joined us earlier. We have our NASA scientists here to answer your questions. So, now I'm getting pinged here. Shaw from Facebook is asking, which exoplanets have water?
Ooh, great question. I can start. So we know of thousands of exoplanets so far, some from TESS, some from Kepler, some from other surveys. And how many have water is a great question. We're just starting to probe that using telescopes like the Hubble Space Telescope, actually. And the James Webb Space Telescope, which should launch in a few years, that will also look for water in planets. So we're just kind of starting the search, but we've identified water in a lot of Jupiter-sized planets so far. And yeah, so I would say maybe tens right now, but they're all Jupiters, nothing quite the size of Earth yet. Anything to add, girls?
No, that was it. I was going to just say, we don't really know,
Yeah.
but you know, but her answer was better.
But you could also say, like, we know of thousands of planetary systems, but not all of them are really the ones that are the right ones to take to Hubble to look for the water. So those are a much smaller subset, and those are larger planets too. So as our telescopes get better, we're going to be digging down closer to Earth-sized planets and hoping that those smaller planets will also give us some signals of water.
All right, we're also getting another question from Twitter asking, where is TESS right now?
Oh, okay, that's a great question. So our orbit is really very elliptical. So we come in close to the Earth and we use the DSN to bring the data down. And we have just completed our 9th observing sector in the southern part of the sky. And we've turned the telescope around to do our 10th observing sector as of the last day or so. So it is on its closer part of its orbit. And it's highly elliptical, but it never gets any further from the Earth than the Moon. So we're still very, very close to the Earth.
And just to clarify, so the way TESS works is it takes like a sliver of the sky, right, at one time, and then it builds like a large profile of what the sky is looking like?
Right, it's going to observe the 85% of the sky when we're done with our 2-year survey in slices that we call observing sectors. And it stares at one slice for 27 days straight without blinking. And then it turns and sends the data down. It actually does that twice in a sector, and then it will turn to the next sector. And when we're done with, say, the first year of our observations, if you were to unfold that, you would see that we had painted these observing sectors on the southern part of the sky.
All right, Andrea from Facebook is asking, what makes Earth habitable, and how can we tell if a planet could even support life?
Aki, I think that's for you.
Okay, well, okay, so again, it's funny, I always want to answer all these questions by starting off, we don't know, and then say about what we do know. Now, okay, so we think about the Earth, and the Earth is unique in the solar system. It's the only planet that has a global biosphere with so much life on it, liquid water and so much life, that life is actually changing the chemistry of the atmosphere, the whole atmosphere. The oxygen in our atmosphere comes from plants, there's methane from bacteria. But what makes Earth habitable? Well, we think, as Patty said, liquid water seems like it's required. But as far as the other things that might be needed, we don't really know.
But we know it would make it uninhabitable.
Yeah, it's more like we know how to kill a planet, basically. But you know, but for all the other things that might matter, in a way, we want to learn about that by studying the planets around other stars.
All right, thank you. I'm really excited to see what TESS is going to explore next. And these discoveries are helping us understand our place in the cosmos. So, speaking of exoplanets, I'd like to introduce someone who knows a lot about this subject, and that is Dr. Thomas Zurbuchen. Thomas is the Associate Administrator for Science at NASA. So, hello, Thomas, and just a basic question, even for my own edification, what does an Associate Administrator for NASA do?
So, together with an amazing team, we run all these science missions we just talked about, including 100 missions looking at the Earth, the planets, the space between the planets, our sun, and then into the deep universe. So we're both setting strategic direction, but also operating those missions. And all these colleagues you've met are, of course, part of that big team.
It really is sort of amazing the breadth of types of science that NASA really is conducting right now. So
it's really amazing. It's
Yeah.
just absolutely stunning.
Yeah, and I'm hoping that we will cover a lot of what that is in this show moving forward.
You should.
Yeah, but I know that you have a special guest with you today, so I'm going to let you introduce her.
Yeah, this is Anna Humphrey, who is at T.C. Williams High School. You're a senior there.
Yes.
Remember the Titans, right? A Titan right here. And of course, you're here because of the amazing work you've done outside of the classroom. And you're a researcher. In fact, you won an award, the Regeneron Science Talent Search Award. And you did research on exoplanets. And just tell us, what did you find?
Yeah, so I was looking at systems where we'd already found multiple planets, and the idea was, is it possible that we're missing more planets in between the ones we've already found? So what I did was I took an imaginary planet, and I wanted to see if I could squeeze it in between two that we already knew about without disrupting the orbits of the two planets that we'd already found. And that disruption would be caused by gravity. So gravity is the thing that pulls us down to Earth, right? So if you have planets that are next to each other, they pull on each other as well. And so I was trying to make sure that that pull wouldn't be so big that it would cause the planets to get ejected from the system or
that's
crash
really cool.
into each other.
So all these planetary systems you have, if you put another one, and in some places they work just fine, and in some other places, what happens?
Yeah, so if the planet is too large or if it's too close to the other ones, they'll pull on each other, and it can actually cause planets to get ejected from a system or collide, do really exciting things that we don't want to happen in a solar system.
Something that may have even happened here or in other planetary systems.
Exactly.
Let me ask you a question, and that is, do you remember the first time you figured out something nobody else knew?
Yeah, so I remember when I made my big sort of discovery in this particular research project. I was sitting in my grandmother's house over Christmas break, and I was trying to figure out how can we figure out if there are more planets here, if we're missing any. And I had this idea of creating a map using math, and that epiphany moment came. And
What an amazing thing. You will never forget that. I never forgot my first moment. Research is amazing, and I hope you'll be a researcher all your life.
Yes, yeah, I hope so too. That's my goal.
Congrats, Anna.
All right, thank you both for joining us. It really is a special thing. I'm so glad that NASA has all this public data that we're doing, that a special person like you can use it and do further research. So that's really exciting. And I want to thank all of you for joining us today. We loved taking your questions and exploring our cosmic neighborhood together. And I just want to remind you that we chose to do this live so that you could become a part of the show and ask your questions that fuel your understanding of the universe. Please join us next month as we take a look at our home, Earth. And in the meanwhile, learn more by visiting go.nasa.gov/NASA Science Live. We'll see you next time.